right, perfect. My name is Andrew. I'm an undergraduate student here at Clemson University. I'm going to be an incoming freshman, and I'm here working on the ARMLab under the YOLO program. So autonomous robots are revolutionizing various industries, from warehouse logistics and military operations to agriculture and mining. Here's an example of an Amazon warehouse robot. And this is a self-driving tractor. In challenging environments, ensuring reliable object detection within the pipeline is critical. However, testing on large-scale robotics is expensive and potentially damaging to the robot. So prior to deploying on full-scale vehicles, testing on small-scale robots within simulations is essential. The VEX AI competition is an ideal testing platform as it provides cheap access to cheap and compatible parts. This year's competition is over-under. So first we started with a simulation. Simulation allows for rapidly accelerated iteration without the constraints of time. It also reduces the possibility for damage to the robot. First, we started with a virtual model assembled in Onshape using the open source VEX files. Then the model was imported. I think on the recording you're not there. So. Okay. And then step 2, the model was imported into the Isaac Sim robotic simulator, and real-world gravity was added. The third step was to make the triballs deformable and fit under the net. So you can see here, the tribal deforms under the net to make sure it fits because it's a little bit taller. The fourth step was programming the robot with the A-star move-to-point algorithm. You can see here, the robot is moving to a point inside of Isaac Sim. So once we were done the simulation, it was time to move to the physical deployment. The physical robot was assembled using traditional VEX parts, with the exception of the Jetson Nano GPU, which is specifically designed to accelerate real-time computing and is used for various AI applications, and the Intel RealSense camera, which uses 2 IR infrared sensors and a dual camera setup to see in 3D. Here's a clip of the robot moving to a point and accounting for a push as well, using the A-star and localization. So this was kind of my area of focus, which was the object detection. Perception through rapid and reliable object detection is crucial to ARs. In order to achieve accurate motion planning and control, ARs need to perceive their environment and localize accurately. Our environment is the VEX AI field, which has a certain number of elements, including the obstacles, the triballs, other robots, and the goal, which is a net. The first method of object detection we looked at was the YOLO algorithm, which stands for You Only Look Once. It's one of the most popular models for object detection, and it employs a convolutional neural network to predict image classification and object location. So this is image classification, where it just says the object is a cat. And this is localization, where it recognizes where the object is. And then combined for detection, it localizes where the image is and the classification, which is a cat. This is an example of what the output of the YOLO algorithm would be, which is a bunch of objects where it can recognize where they are and what type of object they are, allowing it to perceive its environment. So how does the YOLO algorithm actually work? The first step is the residual boxes. The image is divided into a grid, and each cell will be responsible for detecting an object within them. Second step is the bounding box regression, and it has 5 different properties. The first is the probability of the object being within the box. And for the cat example right here, it's a 1, or 100% probability. then the center of the box. And it's divided into x and y coordinates, 0.05 being x and 0.04 being y. Then the width of the box, which just says it's 0.35, and the height, which is 0.4. And then it also predicts the class of the object, which is saying it's a cat and not a pug. The third step is an intersection over union, or IOU. Sometimes several boxes are predicted by the different cells in the grid, as you can see here. IOU solves this issue by accounting for the overlap and confidence scores to predict the final bounding box. It puts the area of the overlapping over the total area to predict a final bounding box. The second method we looked at for object detection, and the one we finally settled on, was OpenCV. OpenCV is an open source computer vision and machine learning software library. Using OpenCV, an algorithm was compiled to detect the triballs. First, a NumPy array is created for color and depth. Then a mask is created where white is true, green, and black is false, which is all the colors. That's in the bottom left-hand corner. As you can see, the white is the green triballs, and the black is all the other colors. From there, from the mask, a contour is drawn. It's in the bottom right here. And then the fourth step is where the bounding box and center were drawn using some of the OpenCV functions, which is in the top left-hand corner. The green outer layer, that box is a bounding box, and then these blue dots are the centers. So in conclusion, we have a robot able to localize and move to a point accurately. It's able to recognize triballs using the Intel RealSets camera. In the future, we'd like to connect the camera to the VEX brain and create a live map of the field. We'd also like to extend the findings toward larger scale robots and in the industry. Thank you.
Great. Dhruv, could you mind stopping the recording?
I got it.